power factor improvement. As we consider the control converters, the important part in these control converters are ripple contents, and this ripple contents depends upon the firing angle. Thus, as the ripple contents increases, the power factor decreases. So it is necessary in these phase control converters to improve the power factor. The power factor of phase control converters depends on delay angle alpha, and it's generally low, especially at low output voltage range. This converter generates harmonics into the supply. The force combination can improve the input power factor and reduce the harmonic levels. Thus, due to ripple contents, the power factor decreases, and the force combination is a method by which we can improve the power factor and also reduce the harmonic levels. These force commutation techniques are becoming attractive for AC-DC conversions. With advancement of power semiconductor devices, the force commutation can be implemented in practical systems. The basic techniques of force commutation for AC-DC converters can be classified as extinction angle control method, second, symmetrical angle control method, third, pulse width modulation, and fourth, sinusoidal pulse width modulation. We'll study these four methods in detail. First, extinction angle method. The figure A shows single phase semiconverter where thyristor T1 and T2 are replaced by switch S1 and S2. The switching action of S1 and S2 can be performed by gate turn of thyristors, that is GTOs. The characteristics of GTOs are such that GTOs can be turned on by applying short positive pulse to its gate, and in case of normal thyristors, and turn off by applying negative pulse to its gate. In extinction angle control method, the switch S1 is turned on at omega t is equal to 0 and is turned off by force combination at omega t is equal to pi minus beta as shown in figure B. The switch S2 is turned on at varying the extinction angle beta. Figure B shows the waveform for input voltage, output voltage, input current, and current through thyristor switches. The fundamental component of input current leads the input voltage and the power factor leading. In some applications, this feature may be desirable to simulate capacitive load and to compensate for line voltage drops. Using this circuit diagram, the average output voltage can be found. The average output voltage can be found as VDC is equal to 2 divided by 2 pi integration 0 to pi minus beta, as switch is turned on from 0 to it's turned on at 0 and switched off at pi minus beta. So integration 0 to pi minus beta Vm sin omega t into d omega t. If we solve this integration, the average output voltage is given as Vm divided by pi into 1 plus cos beta, and Thus, VDC can be varied from 2 Vm divided by pi to 0 by varying angle beta from 0 to pi. Similarly, we can also find out RMS voltage, which is given by equation Vrms is equal to 2 divided by 2 pi integration 0 to pi minus beta Vm square sine square omega t into d omega t raised to 1 half. If you solve this equation, the RMS voltage is given by Vrms is equal to Vm divided by root 2 multiplied by under root 1 divided by pi into pi minus beta plus sine 2 beta divided by 2. Figure A shows single phase full converter where thyristors T1, T2, T3 and T4 are replaced by force commutator switches S1, S2, S3 and S4. The switches S1 and S2 are turned on at omega t is equal to 0 and it is turned off at omega t is equal to pi minus beta as shown in figure B. The switches S3 and S4 are turned on at omega t is equal to pi and turn off at omega t is equal to 2 pi minus beta. For inductive load, the freewheeling path must be provided by switches S1, S4 or S3, S2 and the firing sequences should be switch 1, switch 2, then switch 1, switch 4, then followed by switch 4, switch 3 and last switch 3, switch 2. So this should be the firing sequences for inductive load with freewheeling path. Next method is symmetrical angle control method. The symmetrical angle control allows one quadrant operation. Figure A shows single phase semi-converter with force commutator switches S1 and S2. The switch S1 is turned on at omega t is equal to pi minus beta divided by 2 and is turned off at omega t is equal to pi plus beta divided by 2 as shown in waveform in figure B. The switch S2 is turned on at omega t is equal to 3 pi minus beta divided by 2 and it is turned off at omega t is equal to 3 pi plus beta divided by 2. The output voltage is controlled by controlling the conduction angle beta. Figure B shows the waveform for input voltage, output voltage, input current and the current through switches. The fundamental component of input current is in phase with the input voltage and power factor is unity. Therefore, the power factor is improved by having the switches controlled by switching at the given angle. The average output voltage can be found from the waveform, that is VDC is equal to 2 divided by 2 pi integration pi minus beta divided by 2 to pi plus beta divided by 2, that is switch S1 is turned on at pi minus beta divided by 2 and it is turned off at pi plus beta divided by 2. So integration will be having limits pi minus beta divided by 2 to pi plus beta divided by 2 Vm sin omega t d omega t. If you solve this integration, the average output voltage can be found out as 2 Vm divided by pi sin beta divided by 2. Thus, VDC can be varied from 2 Vm divided by pi to 0 by varying the conduction angle beta from 0 to pi. Thus, we can also find out the RMS voltage using this limit, which is given by equation Vrms is equal to 2 divided by 2 pi integration pi minus beta divided by 2 to pi plus beta divided by 2 Vm square sin square omega t d omega t raised to 1 half. If you solve this equation, the RMS voltage is given as Vm divided by root 2 into under root 1 divided by pi into beta plus sin beta. So, using this method, we can improve the power factor of the semi-converter. Third method is pulse width modulation control. So, if the output voltage of single phase semi-converter or full converter is controlled by varying the delay angle, extinction angle or symmetrical angle, there is only one pulse per half cycle in the input current of the converter. As a result, the lowest order harmonic is third order harmonics. It is difficult to filter out the lower order harmonics. So, in pulse width modulation control, the converter switches are turned on and off several times during half cycle and the output voltage is controlled by varying the width of pulses. So, the shortcomings of the extinction angle, symmetrical angle methods are only one pulse is generated at a time. So, the lower order harmonics, which is third harmonics, cannot be eliminated very easily. Thus, we want to generate many pulses at a time, and it can be done with help of pulse width modulation control. Figure shows the input voltage, output voltage, and input current waveforms. The lower order harmonics can be eliminated or reduced by selecting number of pulses per half cycle. However, increasing the number of pulses would increase the magnitude of higher order harmonics, which could be easily filtered out. The output voltage and the performance parameter of the converter can be determined in two steps. First, by considering only one pair of pulses, such that if one pulse starts at omega t is equal to alpha 1 and ends at omega t is equal to alpha 1 plus del 1, and the other pulse start at omega t is equal to pi plus alpha 1 and ends at omega t is equal to pi plus alpha 1 plus delta 1. These intervals are from the waveform shown in the figure. So first step is by considering only one pair of pulses. Then second, by combining the effects of all pairs. If m pulse start at omega t is equal to alpha m and the width of that pulse is del m, the average output voltage due to p number of pulses in pulse width modulation is found from equation VDC is equal to summation m is equal to 1 to p into 2 divided by 2 pi integration alpha m to alpha m plus del m Vm sin omega t d omega t. Substituting the limits, we'll get the average voltage as VDC is equal to Vm divided by pi summation m is equal to 1 to p cos alpha m minus cos alpha m plus del m. If the load current with an average value of Ia is continuous and has negligible ripples, the instantaneous input current can be expressed in Fourier series as I of t is equal to IDC plus summation n is equal to 1, 3 up to upper limit is infinite an cos n omega t plus bn sin n omega t. Due to the symmetry of input current waveform, there will be no even harmonics and the DC current, that is IDC, should be 0. If IDC is equal to 0, then the coefficient AN and BN of the above equation is given by AN is equal to 1 divided by pi integration 0 to 2 pi I of t cos n omega t d omega t. So substituting the limits, that is an is equal to summation m is equal to 1 to p 1 divided by pi integration alpha m to alpha m plus del m I a cos n omega t d omega t minus 1 divided by pi integration pi plus alpha m to pi plus alpha m plus del m. That means one pulse starts from alpha m to alpha m plus del m, and second pulse starts from pi plus alpha m and it ends to pi plus alpha m plus del m. I a cos n omega t d omega t, which will be equal to 0, and the coefficient bn is given by 1 divided by pi integration 0 to 2 pi I of t sin n omega t d omega t, which will be equal to summation m is equal to 1 to p into 1 divided by pi integration alpha m to alpha m plus del m I a sin n omega t d omega t minus 1 divided by pi integration pi plus alpha m to pi plus alpha m plus del m I a sin n omega t d omega t, which will be equal to 2 I a divided by n into pi multiplied by summation m is equal to 1 to p cos n alpha m minus cos n alpha m plus del m. Thus, by substituting the value of an and bn in the equation of current I of t, since an is equal to 0, we only the value of bn will be substituted in the above equation of current I of t. After substituting, the current I of t as I of t is equal to summation n is equal to 1, 3, 5, 7 to infinity. Substituting the value of bn will get under root 2 in sin n omega t plus phi n, where phi n is equal to tan inverse an divided by bn and in is equal to an square plus bn square raised to 1 half divided by under root 2. The fourth method is sinusoidal pulse with modulation. The widths of pulses can be varied to control the output voltage. Suppose if there are p pulses per half cycle of the same width, the maximum width of the pulses will be pi divided by p. The widths of the pulses could be different. It is possible to choose the width of pulses in such a way that certain harmonics could be eliminated. Thus, by controlling only the width of pulses, we can eliminate the certain harmonics. There are different methods of varying the width of pulses, and the most common one is sinusoidal pulse with modulation. In sinusoidal pulse width control shown in figure, the pulse width are generally generated by comparing a triangular voltage VR of amplitude AR and frequency FR with half sinusoidal voltage VC of variable amplitude AC and the frequency 2 Fs. The sinusoidal voltage Vc is in phase with the input phase voltage and has twice the supply frequency Fs. The widths of the pulse are varying or varied by changing the amplitude AC or the modulation index M, where modulation index is defined as M is equal to AC divided by AR. In sinusoidal pulse with modulation control, the displacement factor, that is nothing but power factor, is unity. The lower order harmonics are eliminated or reduced. For example, with 4 pulses per half cycle, the lowest order harmonics is fifth, and with 6 pulses per half cycle, the lower order harmonics is seventh. Thus, by increasing or decreasing the width of pulses, we can eliminate the certain harmonics present due to the phase controlled converter. So these are the four methods by which the power factor and the harmonics power factor can be improved and harmonics can be eliminated.